Okay, so in this video, we're going to talk about composition of functions and inverses of functions. So what is a composition of functions? Composition of functions involves more than one function, kind of like a system of equations. It involves more than one equation. This involves more than one function. So what we're saying here is that in a composition, the output of one function becomes the input of another function. You can do this with several functions or just with two, and we're going to start really just with two. Okay, so let's think about this for a second. There are lots of examples of composition of functions in the world around us, okay? If any of you have ever done your laundry, this is a composition of functions, okay? We have the input, which is our dirty clothes. We're going to put this into the first function. The first function is the washer. What comes out of the washer? Clean, wet clothes. So this is the output of the first function. But we're actually going to take these clean, wet clothes and we're going to put them in the dryer. And that is going to give us clean, dry clothes. So the output of one function becomes the input of another. So these clean, wet clothes go into our second function. So it's an input again. Our second function is the dryer. And out comes our clean, dry clothes. So this is a composition of functions. Okay. We have this all the time. Let's take another example. We have a set of ingredients. Where do we put these ingredients? Into a mixer. That's our first function. What comes out? Dough comes out. Where are we going to put that dough? We're going to put it in the oven. And what comes out? Our bread. So this is the output of the mixer, but the input of the oven. Okay. One more. Coffee beans. Where do we put this? We put it into a coffee grinder. What comes out? Coffee grinds. So the output of the coffee grinder becomes the input of our coffee pot. And what comes out? Our coffee. Okay. So once again, the output of one function becomes the input of another function. Okay, so how did this work? Let's take this using numbers. Let's take functions, mathematical functions. Let's say that we had f of x is equal to 2x plus 1, and g of x is equal to x minus 3, okay? Well, if we're going to compose these, then we're saying, okay, let's create an input, okay? Let's say, so first of all, composition, there are two different ways that we could write it. This is kind of important. Two different ways that we could write it. We are saying, remember, g of x together is an output. The inputs of each of these right now are x. So what we're doing is we're going to say, okay, well, instead of the input of one of these functions being x, we're going to make the input the output of the other function. Okay, just in case that was confusing, let's write it. Instead of the input of f being x, the input of f is g of x. Right? What goes inside the parentheses is is your input. So what we're saying here is the output of g of x, because that's what g of x is the input of f. That's what we've done. The output of g becomes the input of f. Okay, there's another way that we could write this. We could also write this as f following g of x. It means the same thing, it's just a different way of writing it. Okay, it's really the same amount of writing. It's just two different ways of writing it. People like this method because when we do other things in mathematics, this word following, this little circle that you see here, that's used in other areas of mathematics too. Okay, and the idea is that you do something to something, and then you take what you got, you take your result, and you do something new to it. Okay, so that's what this is doing. It's saying, okay, you put in an x, you get something, you do x minus 3, so you've done something to it, and then now you're going to take that new thing and you're going to put it into f of x. Okay, so let's see how this works. Let's say that we want to know f of g of 2. This says you're going to put it in g first, and then you're going to take that result and you're going to put it in f. So what we're doing really is we're saying, okay, we're going to put 2. We're going to put it into g. So g of 2 is equal to 2 minus 3. Right? This is our function. What comes out? A negative 1. That negative 1 is now going to go into f. So it's not f of 2, it's f of negative 1. And we get 2 times negative 1 plus 1. And what comes out of this also happens to be negative 1. So f of g of 2 is equal to negative 1. Let's say that instead we did f of g of 1. Okay, so now we're going to take 1 and we're going to put it into g first. So 1 is going to go into g. What comes out? Negative 2 comes out. Now negative 2 is going to go into f. And what comes out of that? -3. So that means that f of g of 1 is equal to -3. Okay, we could go the other way as well. So we don't just have of x. We could do g of f of x. So we'll use, I'll put this up here again just so that we have it in front of us when we do this. F of x equals 2x plus 1. G of x equals x minus 3. Okay, and this time we're going to find g of f of x. Okay, or another way of writing it, same thing, g following f of x. Okay, so let's find g of f of 1 again. Except this time, our 1 is going to go into f first. So 1 goes into f. So we're doing f of 1, which is 2 times 1 plus 1. What comes out? 3 comes out. Now this is going to go into g. So g of 3 is 3 minus 3. So what comes out? 0. So f of g of 1 is equal, g of f of 1 is equal to 0. So you can see actually that order matters. F of g of 1 and g of f of 1 are two different things. F of g of 1 is -3. G of f of 1 was 0. Okay. Okay, here's the thing though. If you have to do this with a lot of different numbers, right? If I wanted to give you f of g of 2, f of g of 3, f of g of 7, f of g of 10, this is going to start to get really cumbersome. So what we can do is we could actually put one function into another to create a new function, okay? So that we only have to plug it in once. So let's do that. Let's say that we have f of g of x. And we want to find what that is for all x's, okay? Well, here's what that means. That means take your x minus 3 and stick it into f. Put it inside of f. So every time that we see an x, we're going to go through the f. So we go through the outside function. And every time that we see an x, we replace it with g of x. Every time, that's what this means. Every time we see an x in our f of x function, replace it with g of x. Okay, if we were doing g of f of x, which we'll do in a second, it's the opposite. Every time that you see an x in g, you're going to replace it with f of x. So here, first thing that we see in f is 2. Then we're replacing the x with g of x. So instead of x, we're going to write x minus 3. And we keep going through this function and we see a plus 1. And we could simplify this. This becomes 2x minus 6 plus 1, or 2x minus 5. Okay, so we have two pieces here. This is f of g of x. This is f of g of x in simplified form. If we wanted to do g of f of x, So this time, as we said, every time we see an x in g of x, we're going to replace it with the f of x. So for this function, it's x. We see an x, so we're going to take that x, and we're going to replace it with the 2x plus 1. And then minus 3. So 2x plus 1 minus 3 is 2x minus 2. And you can see if we plugged in 1, okay, instead of doing it this way, we could plug 1 into this function. 2 times 1 minus 2 is equal to 0. If we plugged 1 into this function, we would get 2 times 1 minus 5, which is equal to negative 3. And that's what we got when we did it in this way. Okay, and what this does is it makes it much faster, because now if we want to find g of f of 2, we don't have to go through this process again. We could just do 2 times 2 minus 2. Okay, so let's do this with a bunch of different functions. We'll do it a few times, all different kinds of functions. Let's say that we have given f of x equals x squared plus 2x plus 1, and g of x is equal to 3x minus 4. Okay, we're going to find first f of g of x, and then we'll find g of f of x. Okay, f of g of x. Well, we go through and we say, notice we're going through the outside function. So we see an x right off. That x is now g of x. That g of x was squared, so that x was squared, so g of x is squared. 3x minus 4 is squared. Now we're going to do that in the second x as well. So we have a plus 2, and then we see an x again. So we replace it with 3x minus 4. And then we have a plus 1. So every time we saw an x, we replaced it with g of x. And now we can do the same thing, except the other way around. Now we're going to look at the g of x and replace the x with f of x. So I see 3, and then I see an x. So instead of x, we're going to write x squared plus 2x plus 1. And we see a minus 4. Okay, you can simplify. I don't want to take the time to do all of the algebra, but remember 3x minus 4 squared is 3x minus 4 times 3x minus 4. You cannot distribute this square, okay? You can't distribute it inside here because this is an exponent on the outside, subtraction on the inside. That's more than one level away. Remember our order of operations, okay? Here you would just distribute the 3 and combine like terms, okay? Okay, let's take another one. This time, let's say f of x is equal to x cubed minus 4. G of x is equal to x plus 2 squared. So let's find f of g of x. Remember, you've done this before, actually. You did this when we did difference quotients, right? Your g of x was just x plus h. So here, we're looking at the f. We see an x cubed, so instead of x, we have an x plus 2 squared. Okay, now that's cubed. And then minus 4. Okay, so it's messy here, but that's okay. So just remember there, you would put parentheses around your x plus 2 squared. Now we can do it the other way around. We're going to do g of f of x. So this time, we're going to go through the g, and every time that we see an x, we're going to replace it with x cubed minus 4. So we have our parentheses, and then we see an x. So x becomes x cubed minus 4. Then we have a plus 2. And that whole thing is... Okay. Let's take another type of function. This time let's do different... I'm going to stick to polynomial functions, which I know we haven't really talked about polynomials yet, but these polynomial functions are these functions where you're seeing these powers. Okay. Sorry, this computer is running a little bit slow, probably because there's a bunch of stuff going on. Let's say that we have f of x is equal to x squared plus 2x minus 3, and g of x is equal to x minus 4. Okay, let's do f of g of x. So we go to the f of x, we see our x's. Every time we see an x, it's replaced with x minus 4. So we have x minus 4 squared then we have plus 2, and now we have another x. So we have another x minus 4. Notice it's replacing what we have. Okay, again, I apologize. This is running a little slow. So 2 times x minus 4. And then we still have a minus 3. Don't forget about that minus 3, okay? The most common mistake is you get so caught up in replacing that you forget about the ends of the functions. And then finally, we have g of f of x. So instead of x, we're replacing this with f of x. So x squared plus 2x minus 3, and then minus 4. Okay. You may be asked to simplify these. If you are having a lot of trouble simplifying the algebra, please contact me, okay? Okay, so this is composition. We have a flip side to composition. We have something called inverses, and it's going to seem like they're very unrelated, and then you're going to see that they're actually very, very related. So an inverse function is, we can describe it as in 2 different ways, okay? So inverse functions are actually taking the function and reflecting it in the line y equals x. Okay, so think of your axes. This is the line y equals x. And if I take a line, I'm going to keep this kind of simple because it takes a little bit of talent to be able to do this visually. So we'll keep this simple. Let's say that I have just this line here. If I were to take this line and reflect it in y equals x, what happens is it just winds up on the other side. So this would be the inverse. Right? It just winds up on the other side of the line. Think of it like a mirror. So if this is f of x, then this would be the inverse of f of x. Y equals x is a mirror, okay? Now, there are some restrictions to this. The restriction is that, actually, I'm going to wait for this restriction. Let's first find the inverse, okay? So the way that we describe the inverse is we use something called we use a little -1 at the top, okay? So inverse of f of x, the way that we would write it is like this: f with a little -1 of x, okay? So the inverse, this is the function notation for inverse. It's with a little -1. This is said as f inverse of x. When we do trigonometry, you'll see this again. It is not being raised to the -1 power, okay? And it's really important that this -1 goes between the f and the x, okay? It can't go after the x. It can't go before the f. It has to go in between. Okay, so how do we find inverse? Well, inverse is essentially saying one function undoes the other. Suppose I asked somebody, imagine sitting in a classroom, and I asked somebody to get up, go to the door, and turn off the light, okay? That would be a function. The inverse of that function would be for that person to turn off the light, walk back to their seat, and sit down, okay? So I want you to notice something. Stand up for the function for turning off the light. Stand up, walk to the light switch instead of the door, since we don't know where it is. Turn off the light. Let's say that this is the function. Well, the inverse of that function, f inverse of x, would be saying turn on the light. You're undoing what you did. Think about it like you're playing a video, but you're rewinding it, okay? You turn on the light. You walk back to your seat. And then you sit down. So what are you doing? You're doing the opposite action, but you're also doing it in the opposite order. So for example, if f of x were equal to 3x minus 5, f inverse of x would be saying, okay, Well, in order to do this, the first thing that we did is we multiplied x by 3. Then we subtracted 5. So the inverse would be opposite operations in opposite order. So what we did last now becomes what we do first, and we do the opposite thing. So instead of subtracting 5, we add 5. Instead of multiplying by 3, we divide by 3. So what is this? X plus 5 divided by 3. Okay, here's the thing though, right? This could start to get pretty confusing. This could start to become a very long process, and it certainly isn't something that a lot of people can do. So there is another way to do this, and it's based on the fact that it's a reflection in the line y equals x. So let's talk about how to find the inverse, and we're going to keep it simple. We're only going to talk about linear functions. Those are pretty straightforward in terms of finding the inverse. At another point, we'll be talking about inverses of other functions. Okay, so finding inverses of linear functions. Well, it's a reflection in y equals x. So that is telling you what to do. A reflection in y equals x says y equals x, x equals y. So you have f of x is equal to, let's take the same function that we just did, 3x minus 5. And the first thing that you're going to do to make your life easier is you're going to change the f of x to a y. Remember, it's the same thing, it's just that the f of x tells you it's a function. Okay? So that's your first step. Your second step is to actually reflect it. So to reflect it, your x becomes y and your y becomes x. So you're switching x and y. What does that mean? You're literally just switching it. X equals 3y minus 5. And at this point, this is the inverse. You found the inverse. It's just that we don't like the inverse in that format. So this is the inverse. So now our last step is just to solve for y. Because then we can actually graph it. We're adding 5 here. We get x plus 5 equals 3y. And then we can divide both sides by 3. And we get that y is equal to x plus 5. Over 3. And then your very last thing is replace the y with f inverse of x. And the reason for doing that is to indicate that it's the inverse of your original function. It kind of says, okay, we're done. Okay, so replace y with f inverse of x. It's telling you how the two functions are related. Okay, let's take another example. We're not going to do too many of these because it's always the same thing. Let's say that we have f of x equals x minus 7 over 3. Okay. So what do we do here? First, change your f of x to a y. Then we just multiply everything by 3. Because we have to solve for, oh, I'm sorry, I messed up there. Right? I forgot our second step. We have to switch our x and our y. So x is equal to y minus 7 over 3. Okay, so we switch the x and the y. Then we can multiply everything by 3 because then we're solving for y. So that gives us 3x is equal to y minus 7. Add 7 to both sides. And we get that y is equal to 3x plus 7. And I just preference, I kind of like the y on the left. So when I do the replacements, that last step, replace y with f inverse of x, I'm going to put that on the left. It doesn't matter. Okay, so once again, what did we do? Here, we just replaced f of x with y. The reason for that too is that when you switch your x and your y, you don't want to switch x and f of x. That would be really confusing, okay? So that's why we do it this way. Switch x and y. Solve for y. And replace y with f inverse of x. Okay, so a couple of last minute things here, just important, that relate the composition of functions to the inverses of functions, okay? So inverse says one function undoes another. So what does this mean? This means that when we put one function inside of another, it's as if we've done nothing. Go back to the idea of the light switch, right? If I said, get up out of your seat, go to the light switch, turn it off, and then I asked you to then turn off the light, turn the light back on, come back to your seat and sit down, it's as if you never left, right? It's as if you never did anything at all. So this is what we mean by composition of functions. When we take that one function and we put it inside of the other, it's like nothing happened. So when we take this x, we multiply it by 3 and then subtract 5. And then we take that and we add 5 and then divide by 3. It's as if we did nothing to the x at all. When we compose inverses, they undo each other. And we get x. This is how we could check if two functions are inverses. This means f of f inverse of x is equal to x And it works the other way around. F inverse of f of x is equal to x. Okay, so what does this mean? If we have 3x minus 5, so f of x equals 3x minus 5, f inverse of x we found to be x plus 5 over 3. If we compose these two functions, what happens is let's actually stick it in here. We have 3. Then instead of x, we're going to put in f inverse of x. So we get x plus 5 over 3. And then we have minus 5. Okay, let's simplify this. The 3 cancels out, okay? You have to put in the step. The order here matters, okay? Because the 3's cancel before those 5's cancel each other out. They're inverses. Yes, this worked, okay? It works the other way around as well. Let's take different functions. Let's say we have g of x equals, and let's take the x minus 7 over 3, and g inverse of x, this is the one that we just found, as 3x plus 7. Okay, so these are inverses, yes. These we know to be inverses. We should get x. Let's do this as g of g inverse of x. So you can do it in either order. You'll get the same thing. So here we see an x as our first thing. So we replace that x with 3x plus 7. Minus 7. Over 3. So again, the order matters here. The 7's go away first, and we're left with 3x over 3, which is equal to x. So yes, these are also inverses. Okay. Let's take one more example. Let's say that we had h of x is equal to 2x plus 1, and we said h inverse of x is equal to x over 2 minus 1. Okay, let's compose these two functions and see if they're inverses. So let's compose it the other way, just so that you can see it both ways. Okay, so now we're going to take the 2x plus 1, and actually I won't do it the other way. I'll do it as the h of h inverse, just because the algebra is a little bit simpler. And I want you to see it easily. So let's do h of h inverse of x. But it doesn't matter which order you do it in. That did not. Okay. Okay. So we have a 2. Then this gets replaced with x over 2 minus 1. And then we have a plus 1. So this 2 has to get distributed. So 2x over 2 is just 2x. It's just x. And then we get minus 2 plus 1. Well, this is an x. This is x minus 1. These are not inverses. So we can check to see if two functions are inverses by composing them. If we get x, then their inverses. A couple of other things to know. F of F inverse of 2. Remember, when we take inverses of compositions, our answer is just to x. This tells you what our x is. We don't have to do any calculations at all. F inverse of F of negative 6. We don't even have to know what the functions are. It's negative 6. If I told you that we had K of K inverse of 3, we already know what that is. It's 3, right? These match. 2 and 2, negative 6 and negative 6, 3 and 3. It doesn't matter what function. So notice I've been using different letters. That just says it's g of x is not the same as f of x. That's all. It's like when you use different variables. Okay? Okay. One last thing about inverses. Not every function has an inverse. Okay? The only functions that have inverses are ones where the reflection in the line y equals x is also a function. And there's an easier way to look at this, but this is one of the ways that we determine whether a function has an inverse. So only functions whose reflections in the line y equals x are also functions have inverses. So every function can be reflected in the line y equals x, but they're only called inverses if that reflection is also a function. Okay, so for example, if we have a parabola, we'll take a very simple function. So this is f of x. Its reflection in y equals x looks as follows. So don't forget to label your axes. This is its reflection. This is not a function. I'm going to redraw this because it didn't come out looking like a function. Okay, there you go. Okay, this is the reflection in y equals x. But this is not a function. So we wouldn't call it an inverse. Okay, we can see it's not a function. Any vertical line passes through the function twice, right? Fails the vertical line test. Now we have a way of testing for this without having to figure out what the reflection looks like, okay? It turns out that we don't have to draw the reflection because all we have to do is perform the horizontal line test. If a function passes both the vertical line test and the horizontal line test, then we know it has an inverse. its reflection is a function. We call it a one-to-one functions, okay? So only one-to-one functions have inverses. Okay, so a one-to-one function passes both the vertical and the horizontal line test. Okay. What we're saying is for every input, there's only one output. That's the vertical line test. But it also goes the other way. And for every output, there is only one input. So we talked about this when we originally defined function. Let me see if I can go back and find that. If you notice here, right, we talked about functions and we said, okay, this is a function because every input has only one output. And that's true, this is a function. This is also a one-to-one function because every output only connects to one input. This one we also said is a function. Every input connects to one output. This is not a one-to-one function because 7 has 2 inputs, okay? And one-to-one says every output also has 1 input. If we go to these examples, this is an example, this we said is not a function, so it's irrelevant. This is an example of a function, right? We don't have any repetitive x values, but it's not a one-to-one function because 0 repeats. So now we're looking not just at the x's, but at the y's. This line is a function. It is also one-to-one. It would pass horizontal line test. These two are not functions, so we don't even bother looking at it, okay? So here, this is a function, but it doesn't pass the horizontal line test. So it's not one-to-one. Sometimes you'll see one-to-one written as 1-1. Okay, that's another way of writing one-to-one. And just so that you have some idea of the real world, okay, examples of one-to-one functions would be a person and a social security number. And this is assuming no identity theft, obviously. Each person, security number, or each U.S. citizen, right? Each U.S. citizen has one social security number, and each social security number belongs to one person. An example of a function that isn't one-to-one, a vending machine. This is not a one-to-one function, right? So for a vending machine, you type in a code, you might only get one product, but you might have a product that you could type in multiple codes for, right? Where you'll see Coke in 2 different places, so you could type in 2 different codes. So that would not be one-to-one, okay? A person and fingerprints. This is one-to-one, right? That would be another example. So I want you to try and think of some examples on your own too, because there are lots of examples of one-to-one functions. So that's it. That's compositions and inverses.